Sir, can you switch on your camera? Is it possible?
So I'm in a office.
Okay, okay, no
So
problem, sir.
I'm
No
using
problem,
my
no problem.
desktop.
Yeah, yeah, no problem, no problem. Yeah, before going to start the session, I will give you a brief introduction about the Professor Santha Kumar Mohan. Professor Santha Kumar Mohan got his PhD in robotics and control from Indian Institute of Technology, Madras, in 2010. From June 2010 to 2011, he worked as an assistant professor in the Department of Mechanical Engineering at the National Institute of Technology, Calicut, Kerala. He also worked as a postdoctoral fellow at the Korean Advanced Institute of Science and Technology, Daejeon, in Korea. And in 2012, he joined the Faculty of Mechanical Engineering at Indian Institute of Technology, Indore. He is holding visiting faculty position at IIT Bangalore, BSTU, Belgorod, Russia, KAIST, Division, Republic of Korea, RWTH, HM, and German and ECN, France. His active research areas include service and field robots, specifically the design and motion control of underwater and wheel mobile robots, parallel robotic platform, and assistive and rehabilitation robots. Furthermore, he has received the Outstanding Young Scientist for the year of 2014 from the Korea Robotics Society European Master of an Advanced Robotics Plus Fellowship in 2018 to 19. And also he has received Alexander von Humboldt Fellowship in 2016 to 17 and Satellite Across Virtual Institutes Fellowship from 2013 to 14, World Class University Fellowship from 2011 to 12, and Brain Korean 21 Fellowship from 2011 in 2011. He has published more than 130 articles in various journals and conference proceedings. He has edited 3 books and completed 12 sponsored projects. Currently, he is serving as a technical editor for IEEE ASME Transactions on Mechatronics and associate editor of IEEE Robotics and Automation Letters, Advanced in Mechanical Engineering, ASME Letters in Dynamic Systems and Control, ASME Journal of Computing and Information Science Engineering and Robotica. He is also an adjunct professor at the Department of Engineering Design at IIT Madras and a faculty fellow at the IIT Palakkad Technology iHub Foundation. He is the foundation director of IIT Palakkad Technology iHub Foundation and the Technology Innovation Foundation of IIT Palakkad. In this brief introduction, I am requesting to Professor Santha Kumar Mohan, please start your presentation. Thank you, sir.
Thank you, Ravi. Thank you for the long introduction. So let me actually start sharing my screen.
Yeah, you can share, sir. I gave the permission. You can share, sir.
I think my mic is muted somewhere. Okay.
No, actually, it is not.
Yeah,
Yeah.
it's okay. That's fine. Yeah. So I hope you are able to see the screen.
Yes, sir. Yes, sir. Yes, sir. Actually, I have muted all the mics except you and myself. And
Okay,
for the last 10 minutes, I can switch on all.
Yeah, no problem. That's fine.
Okay.
So let me actually come back the particular interest. So today the session is on design of intelligent controllers. So that is the topic which Ravi shared with me. So I don't know how the serious the talk last 5 days or probably till you can say today. So I thought of giving a brief introduction about a different controllers, how the intelligent controller is different and what kind of scenarios required. And if time permits, I will show some of my research work. Okay. So that is the idea. So because it's 1.5 hours, so I thought I can give a brief idea about this. So although Ravi gave an introduction, so I want to give a very brief about IIT Palakkad. So IIT Palakkad started exactly 10 years back. We are celebrating our 10th year. This academic year is our 10th year celebration. So this institute started in 2015 and we are very young in terms of, you can say, years of experience and as well as number of students. We are only 1,350 students and around 130 faculty members. And we are come under third generation. You might be know that there are seven first generation IIT and then six, you can say second generation IIT. And there are some IIT which we call 2.5 generation because these are converted from, you can say other institution become IIT. And 2015, we started, you can say two third generation, and 2016, four other third generation institutes started. So that is one part. And coming back to my introduction, although he told about me, so I am basically a mechanical engineer. I did a PhD in engineering design, specifically with a specialization on robotics and control. I am actually like a strong believer of, you can say, real-time experiments. So during my PhD time, I was involved two bigger prototypes. So in that, one is actually like a Naval Science and Technological Laboratory, which we call shortly NSTL, Vizag. So this particular DRDO lab had a visionary to develop a autonomous underwater vehicle. So our professor got a project, and I was involved in the controller development. So this yellow color vehicle, which I shown, right? So this is what we call NSTL AUV. This is almost like 4.5-meter long, and the the weight is actually like almost 1.5 ton weight. And this particular vehicle controller I was developing, it's supposed to be, you can say, work up to 600-meter depth. That is the targeted thing. And we could achieve with a very conventional controller. So that is the idea which I want to give a disclaimer. Although we keep talking about advanced, intelligent, all those things. In 2007 to 10, I was involving in this. Even 2010, we did a sea trial with this particular vehicle. So we have developed only simple PID and PD based controller only. That is the background. So later on, I moved to NIT Calicut for a short while, almost 2 semesters. Then I realized that I need to explore my knowledge in different domain. So I moved into KAIST for my research assistant professor position, which we shortly call, you can say, a short-term appointment there. So there I was actually like trying to see if I talk about a field system, specifically service and field robot, there are huge challenges will come in terms of controller. So when you talk about controller, the dependencies again fall on the value, or you can say expertise on the sensing. So I was involving in a sensor fusion integration, and then based on that, the observer, whether it is a state observer or you call observer for a nonlinear disturbance estimation. So this disturbance observer design, all those things are involved, and finally we tried to develop motion controller schemes. So this is the area which I focus. I involved in different robots, but majorly I was involving in a marine robot. So that there also I was involving more on practical side. So the one which is in green color, this is a you can say commercially available US based company underwater vehicle, whereas I was developing one of the vehicle with 8 thruster for a Hyundai industry. So this is the yellow one which you have seen. So this is the way I was actually like doing it. Later on, I moved to IIT Indore, and now I moved to IIT Palakkad. So I thought of seeing what really my scope of research work in faculty position. Then I realized that IIT Indore is central part of India. So I thought, what can be my motto for, you can say, faculty position. Then I realized that I was good at dynamics, and then later part I evolved as a control expert. Then I started a center for robotics and control. So with the interest is robot dynamics and control there. So I started with where I was exposed the service and field robot, specifically on vehicle manipulator system, which we shortly called the mobile manipulator. Then the other side, I was seeing that if anything, talk about robotics. So robotic manipulator is one of the major chunk. In that, if you look at it, we usually say that the parallel robots are having huge advantages. But when you go deeper, the parallel robots are very limited in application. So I thought, why can't put it in a other way around, that how we can expose the or explore the various application of parallel manipulator other than the motion stage or probably simulator. So this is the way I was involving during this course. So our group configured that we can actually like expand this parallel manipulator application into a medical assistive devices. Then I fortunate that we expand our division into a medical assistive devices. So this is the way our group expanded. So that is the bigger thing. So later on, I moved to IIT Palakkad. Then I thought center is actually like very bigger because when I joined, we are almost like 60 to 70 faculty members only. And that time there is no department itself. So I thought, so I start a lab, so where it is focused on robotics. Then I started thinking what can be the name of the lab. Then we found that, so I was working on surveys, assistive field and exploration robot. So then I thought, why can't we shortly call a Safe Robots Lab? So that way we were actually like established Safe Robotics Lab. So then you talk about robots. So we work both conventional and non-conventional robot. So some of the non-conventional I want to show here. So for example, this is a WEG we call, so wheel and leg combination. So this can actually like work in all terrain or probably even in engineering surface. So you can see that this is actually like the same robot can actually like work in a rough terrain, and as well as you can see that even an engineered or it's a staircase. So that is the whole idea which we bothered. The same direction, if you look at it, so several times we need a silent system or probably a rough surface maneuvering system, which we call all-terrain vehicle. So all-terrain vehicle in a normal way, you would have seen that lots of suspension. So when you talk about a small size, you can say one person can carry and launch that kind of vehicle. We call tactical vehicle. So there is a challenge. So we thought of actually like building a passive or active leg based you call mobile robot. So you can see that this robot has a four leg and a four independent wheel drive. So now this leg will act as a suspension and as well as you can say obstacle maneuvering system. So these kind of robotic system which we work other than the conventional service and field robots. So for example, if you look at it, so this particular robot we have autonomously launched and tried to communicate that the robot should go a small top of hill terrain, and then it has to actually like surveillance and then come back. So you can see that the robot is trying to climb, and the stair, or you can say the ramp is very steep. So it is trying to navigate and try to go up. So that way we are actually like working on. So this is one part. So I just want to show like what kind of system we work. So you can see that it is actually like navigating and going on the top, and you can see that after that it is trying to come up after a small surveillance. So this is one part. Later on, we moved into the other side where I was saying no service and field robot. So we developed recently like a two underwater vehicle. One is observation type, the other one is intervention type. So both of them are actually like now technology is transferred, and commercially the manufacturer is actually like make it one of the private company. If anybody is interested to buy also, like you can actually like let me know, I will connect them. So now these two robots are actually like tested in our facility, and then we have transferred. So the whole idea is actually like this is very silent, and you can say like exactly fish like, so that the energy required is less, and as well as it can actually like do different purpose. And this is actually like for an intervention, that means it is actually like involving some operating end, and that particular robot is actually like experimental. The same way we were actually like involving in several defense related projects. So one time actually they have given a task that ammunition handling. So we thought of actually like developing a small ammunition handling which can be put it in the inventory. So later on we found that it takes a long time to get it cleared from the defense organization. So meantime we try to demonstrate that it can be fruit harvesting or vegetable harvesting kind of thing. So these are few service and field robot which we work in our group. And now you can actually like see these are few can say selected project from our BTech students. So you can actually like find that we work from, for example, this is a aerial come ground based robot, or you can see this is a purely aerial robot. So we are working aerial to marine robot, terrestrial to, you can say, space. So these kind of systems we are working. And further, one more thing. So when we talk about our lab, whether it's an internship student or PhD student, they would be involved in a product development apart from their core research, so that some kind of product at the end of their course of degree, they will come up with a product. That's the idea. For example, this is one of you can say intern who came for a BTech project to our group. So we made a small, you can say, rehabilitation robot. Later on, it does actually like send it to one of the Swiss-based company, and then now they are actually like developing their own prototype or product. So these are few, you can say, example how our group is working. Now come back to our original topic, which is design of intelligent controller. So before moving to the topic, so far whatever pictures you have seen, these all actually come from my research. So here after next probably 15 to 20 slides, so which I'm going to show is basically from different researchers and the other resources. I don't want to cite then and there, so I am putting this particular note or a disclaimer. Okay, this is purely for educational purpose. So now come to original purpose. So we are talking about intelligent control, right? So then you should know how the trend has come from either motion or system control. So when you talk about system control, initially it is something like mechanization, or probably some people call feed forward or predefined control. That means the system, when during the development, we know how the system behave exactly. For example, I am developing a conveyor belt. So I'm saying that I start the conveyor belt, and 10th second it reaches the conveying starting point to 10 meter. So exactly it will do that way. So if I am confident in that way, then what happened? So the feed forward control is very easy. Okay? So that what we call a classical control. I'm telling in a different perspective. Classical control means it's a purely model based. So that means it's actually like in mid 80s or mid 70s, where the exact model is known. For example, during the manufacturing itself, we know that this is what happening, and no sensor or no feedback. That's why I said it's a simple open loop or predefined or feed forward control, which is what I'm going to call as a classical control. Don't get confused. What we used to call as a classical control in a control theory, that is purely a transfer function base. So that we will come back in the next slide. So now you know like what our human being started in mid 70. So purely a mechanization. So that is what happened. So you know that, so this point it will happen like this. The next point it will happen like this. It's all predefined feed forward control. So there is a problem, right? For example, over a period. So there is a mechanical part would get wear and tear, or probably the manufacturing can have a defect. So then this classical control, which I call the exact model based control, may not work. So then people try to see is there any other variation. Then people call reactive control, which is what we call so purely a feedback base. So there is no model involved. So heavily involving in a good sensing, which is one of the popular control we heard. This is a three-term control, right? The PID or motion-based control. So this is what the second stage people have brought in. So this was working good in a very, very small level. For example, you have a bigger car, okay, or probably bigger robot. So in an actuator level, this reaction-based controller will work. Whereas if you think about a system level, so each actuator which has contribute a small error that may lead to a bigger problem. For example, you have a serial manipulator. The first motor supposed to be within plus or minus 1 degree, but this actually like accumulate if the series of motor is connected. So at the end, individually each motor would be controlled plus or minus 1 degree. But if you look at the actuator to end effector, the end effector may be having a huge error, probably 10 degree or 16 degree. So then there is a problem. Then what people thought that if anything can be seen, a classical control and the reactive based control can be combined. So this is one of the popular approach we call hybrid control. So where the model based at higher level. So for example, system level, the controller would be designed as a very old classical based. That means some model base would be involved. For example, if I talk about robotic system, so the robotic system, the tentative model I use, then the individual actuator, for example, the motor of each axis or each wheel, I try to control in a reactive base, which is feedback base. So this was working very comfortably in a certain group of robotic or systems. For example, you take about CNC or you talk about simple fixed based manipulator, these are all working good. But when you talk about a system which is very complex, non-linear, or you can say unstructured system, so these are not working. So then people thought about how we can actually like make it happy to work. So there are two problems will be encounter. One is so the uncertainty in the model. Then the second thing is limited in sensing, or the sensor will have a noisy or other thing. Okay. So if you put these two are in front, so there is a bigger problem. So what you need to know, so you need to see, so how to predict. For example, you have a limited sensing. So I have a sensor for only for velocity measurement. Can I actually like you can say find the displacement or position? Yes, I can do. Then I can actually like integrate once and then do it. But when I am doing integration, then I need to have some model so that I can predict better. And second thing is the sensor will not give all the time the data perfect. So then I have to actually like see that. So based on the previous data and what coming currently, I can actually like predict better. So like that something evolved. So that is where we have called a probabilistic based controller or Bayesian based controller, which very popularly known probabilistic controller. So this came in mid 90s, but the problem here is actually like the probabilistic, for example, I call EKF based or particle filter based controller schemes. So this required high computation and data storage, and because your particle density, no. So how, for example, you are using a particle filter as the estimator. So the number of particles are actually like make sense. So then there is a problem, right? So during the same course, there is another control strategy has come, so which is we call expert system or knowledge based control, right? So that had a huge problem because so there is a huge database required, and it is purely based on rule based. So for example, I conduct 1,000 experiments, so those 1,000 experiment data I fit it. So now I'm encountering new situation. I will actually like see that out of these 1,000 anything very close to this. If anything close, I will choose from there and I try to control. So this is one of the bigger control during 90s or 80s, 85 to 95. This is very popular. Even during that time, people even make a fun. For example, if you go to Japan or Korean, so they make the robot and then they try to develop the control scheme. So that means they actually try to run open loop system and then realize how the system works. From there, they actually like make it, you can say, the reverse based control, which is what we call expert system based or knowledge based control. Whereas if you go to a Western country, for example, Germany or France, so they try to develop a mathematical model, try to understand the system behavior, then they try to develop a controller. So this is another stage. So now where we stopped, actually like the probabilistic based on estimation and all. In that case, the integration of model and sensing is seamlessly done. Even inaccurate model and limiting sensing would be fused, and it was good. But still the performance is actually very poor. So people try to see is there anything better. So that time actually like fortunate or unfortunate that the computer were actually like very popular, and the computing facility was actually like better. The GPUs are start coming, then people try to broad a data driven model, so which is what we call learning based control. Now I am actually like going to call that as an intelligent control, because if you look at it, is even 85 90s and all, the intelligent control is purely based on something like soft computing based controllers. So for example, if you talk about Even Professor Begra wrote a book on intelligent system control. It purely start from neural network, then fuzzy logic based control, then weighted based and weighted less. Those kind of approaches would be done. It's all actually like you call simple, you can say compensation controls. But now we are actually like moving towards the data driven, that to learning based control. So that is where we are actually like defining intelligent control. So that is where I'm actually like putting in a progression of control techniques also. For example, the transfer function based simple linear ODE based control, which we talk about in 80s. So this is what we call classical control. Then the improvement on controllability has come. Then people thought that why can't we use a state space where matrix and vector based, and that become a nonlinear. Then they thought that why can't we use the soft computing? Then they brought the introduction of fuzzy factor or neural network. They brought the knowledge based control, which is we call the knowledge control, which was in 2000, 2010 all ruled. And when the 2015 or 16, the learning based control popular, that is where we are actually stuck. That is what we call intelligent control. When you tell these things, so you should know like what really the intelligent control. So in that sense, so we will recall what the human being is doing or any animal is doing. So you all know that. So whenever the baby or something is the living being is formed, the first thing realization in the mother womb would be the one cell. That one cell will start, you can say, beating. So that means the heart cell will start coming in the mother womb. So since then, nobody has planned, nobody has developed or designed a controller, but the heart and the entire system evolved. So any one cell started in a mother womb, so it knows that. So when some situation comes, how to behave. For example, the baby is actually put it in a cold climate, so it starts shivering so that the body temperature increase and come back. So for example, the kid is running for a sprint. So after that, the breathe will have a problem. Then you can see that. So the body will start sweating, and then so long breath will happen, and kind of, you can say, activities coming by default. So there is no design to happen. So then you can think that how nature gave intelligence to individual systems, that could not happen with machines. So then what we can try? We can try to imitate what the human being or how the nature brought towards the, you can say, human being or the living biosystem that we are trying to extract. So this particular idea, what we call artificial intelligence, because we are inducing the intelligence based on the bio inspired system. Okay. So if you talk about this, so then there are actually like several subsections, right? So the AI is actually like having several learning schemes. So one of the subset which we call machine learning. So this would be involved a purely algorithm that enables a computing system or computer to learn from the data which you provide and make decision accordingly. So then what would be the difference between machine learning to deep learning? It is actually like further deep one, because the specialized subset of ML that uses multi-layer neural network, so that you can actually like process larger data set in a shorter period and solve very complex problem and give better solutions. So this is the way the AI become machine learning become a deep learning. Then you can actually like see the same thing, you put it in a improvement by, you can say, corrective action. So you see ML and DL, so it is actually learned from the data set, but if you put a some penalty, or you can say some kind of benefit, and try to derive your objective, that become a reinforcement learning, the ML paradigm only. Whereas the agent learn by interacting with an environment and adjust and optimize its own action through based on rewards and penalty. For example, I want to go outside this room, but there is an obstacle. When I hit the obstacle, I say, hey, you are actually like taking out of your energy 10%. But if I'm actually like putting my step in a, you can say, empty place, so I put probably like 5% energy saved. So like that, I put a reward and penalty. So then what happened? I try to optimize and see how better I can do it. These are all going to happen in, you can say, real time. So then that is what we call reinforcement learning. So now you know, like, so different techniques in learning. So ML, DL, and reinforcement learning, right? So now we will go back to the original purpose. Before going to the original purpose, so I want to actually like give a different ideology on the type of AI. So you know there are two type of AI. So one is analytical AI. So the other one is operational AI. Whereas analytical AI is actually based on the data set. It can give, for example, now you are actually searching in your Facebook or probably in Amazon. So today you are searching something. So when you open next time, so the options will put it in front of you in that screen. So what you call the analytical AI. It is based on your, you can say, the previous attempt, and you can actually like make the decision. So it's all actually like kind of predictive in nature. For example, machine failure or recommendation in your, you can say Facebook or Instagram or probably Amazon. So these all based on, you can say, like the focused data processing, you will be getting the recommendation or some kind of decisions. But what we are actually like focusing, which we call intelligent control, which is very similar to a other subset. For example, you talk about autonomous car or controlling a spacecraft through AI technique. This is actually like you are involving in a physical environment and taking a decision based on the experience which is you are going to get then and there. So that is what we call operational AI. So it is actually like acts on data to perform real world actions and manage physical system. That is what I already told. So autonomous driving or factory automation. So these all actually like what we are calling operational AI. So now you got that the intelligent control can be analytical AI based, then that is actually very systematic. That is not we are attempting. We are trying to attempt the operational AI based controller. That is what we are calling the intelligent controller. Okay. So now when you talk about design, so before that you should define and you have to see what is the difference between individual control schemes already popular, right? So when you talk about why intelligent control system, then definitely you have to ask from the classical, which is the normal non-intelligent control, right? So the non-normal control, which we have seen. So what the bigger problem? You have to obtain the model of the plant, which is to be controlled. So which is purely a model based. Whereas the intelligent control, you does not require any of the model, how it is actually like behave. So based on the experience, you are actually like a trying to correct and then control. Indirectly, one is actually like a plant model or some kind of known thing you're trying to play. Whereas here, based on the experience or the behavior, you're trying to develop. So in that sense, so one is actually like a conventional basis. So you sense, process, and act, which is what the classical cycle. Whereas the intelligent, which is actually like a behavioral or a non-classical cycle, you teach, learn, and behave. So that is what we are trying to see. For example, a classical controller based on mathematical model of the plant, whereas the intelligent control is coming from the plant behavior. If the plant behave differently, the control scheme will adjust, the algorithm will retune and then behave better. That is what we are actually like trying to call intelligent control. When you talk about so intelligent and classical, so one is mathematician approach, whereas the other one is we simply call lazy man's approach because it doesn't require any mathematical or analytical relations. So it is purely you take the system and run the system, see the behavior, and then you develop. So indirectly, the intelligence fall on the designer. Now you can actually like change the intelligence come from the software. So that is the whole idea from classical to intelligent control. For example, in a classical control, the software is fixed. So the designer or the designer of the controller, so would be actually like say that, okay, this is what my controller, this is the sensor data. If the sensor says this much thing, so you act or you actually like give command to your actuator like this. So this is the way it is all there indirectly inside the software. The command is predefined. So if it is actually 10% error, so you can say 5% of control action. If it is actually 20%, 10% control action. Like that is all predefined based on the system. Okay. Whereas the intelligent controller is different. So the behavior and the corrective action is happening then and there based on the existing data and based on the happening what is on the current. So that means the software is actually like evolving based on the design. So that is what we are actually like trying to see. So whereas the classical controller, the designer based on the software, he readjusts all the parameter. Whereas here the designer is actually like trying to readjust the algorithm so that it can work better. That is what we are trying to see. So if I put that way, then immediately some of you can ask, sir, soft computing is actually like very known technique. In that the expert system is one of the popular thing. This is also very similar. Yes, I do agree. So the knowledge-based control system, or some people call expert system, definitely this is very similar based on the existing data or the data set it is happening, which is a heuristic control algorithm, definitely. But what different here is this is purely rule-based approach. If then, and the algorithm is not that flexible as what we are seeing into intelligent control. So here actually the decisions are all very diplomatically put it. The learning is very limited and this is very well suited for a defined problem. Whereas the intelligent control is in adaptive and autonomous in nature where it's purely data driven and algorithm based. So here HS self-evolving as the key, which play a bigger role. So although the fuzzy logic or neural network is going to play, which is there in the back end of knowledge base, but here the overall algorithm here is self-evolving. In the knowledge base, the self-evolving was not there. Okay, so that makes the system to learn and adapt in a real time. Okay, so that is what we are actually like calling as a intelligent control. If I put that way, there are several differences between, you can say, classical knowledge based control to the advanced intelligent control system. So one is AI driven, whereas the knowledge base is purely rule based. If then kind of rule based, the expert knowledge is built on, so it is not changeable. Whereas the intelligent control, it is AI driven, so the learning and adaptability is there. So if you put that way, the application where the knowledge base is very popular for a fault diagnosis, whereas the intelligent control is actually like very popular for the robust robotic control or autonomous vehicle thing. So look like the transparency look like a black box because you don't know how the evolution is going to happen in AI driven control algorithm, whereas the knowledge base, it is very explainable because the rule you are only feeding it. Okay, so now if you put that way, when and where to use that, you can actually like easily understand. The decision transparency is crucial, then you can put knowledge base, whereas that is not crucial but the adoption is very crucial, then you can think about intelligent control system. If the environment is dynamic and uncertain, then you can definitely use intelligent control. And the system is like in the modern days, right? So everything is completely non-linear and the explicit model is not available, then you can definitely use the intelligent control system. Okay, so that is the whole idea which brought. So now we know the intelligent control definition, right? So what really the intelligent control is going to do? So there are three things it is fusing. Okay, so the automatic control is one of the, you can say, bigger section in electrical or control community. So the automatic control and you can say optimization through operation research, these two fuse and evolved based on the algorithm which is come from the soft computing or AI based. So these all three fused where the nature brought as intelligent control. So that is where we can see there are three-way connected the intelligent control. So the automatic control scheme, which is the conventional control scheme, also can be brought in, but that parameter would be adjusted based on the optimization. Then you can ask it is optimal control, but this optimality or the optimization scheme would be evolved then and there based on the, you can say, soft computing scheme. That's why it is called intelligent. Otherwise, it can be simply raw, you can say optimal control, or it can be simply called automatic control. Okay. So now, if you talk about intelligent control design, so then you know, like there are many things I told, right? So then you have to know, so what kind of advanced algorithm you can use. So you have to leverage that, and what kind of technology you have to enhance to make the decision making, and how you can actually use those technology to adjust your parameter and adapt your nature, and you can actually like fine tune your performance of the control system. So in that sense, there are several questions we have to ask. Then you think about a simple control design. What you need system dynamics, right? But here we are not doing that way, right? So when you talk about a very simple control design, so when I ask, so what we used to do, even you recall your control design course, so we will try to plot it in, you can say Bode, Nyquist or Nichols plot, or probably root locus, and then we see how the open loop system work. Then you add the closed loop and see again the performance, and then you try to adjust all those way you did, right? Even in a linear control system. But now imagine we are actually taking away all those things and say that you design control algorithm. So then you have to actually very clear, right? So then it's purely depends on what data you are going to feed and how your algorithm is going to play in a crucial role. So for example, when you think about your algorithm, so your algorithm is actually like very good, but your data set is very poor. So then also your control algorithm won't work better. The other way around, vice versa, your data set is actually very huge, but you don't know what this data set, your algorithm is actually very minimal in terms of, you can say, approaching. So then also it is not good. And third thing, when you design and implement, a bigger problem will come how you can say implementable in a low cost processes. For example, when I involved in Amazon robotic challenge and picking challenge, so we had a bigger problem on, you can say, image processing. That too, like you can say AI based image processing. So then we have used almost like 5 GPUs. Each GPUs were actually like cost around 10 to 15 lakhs. And the overall solution at the end, it went beyond 1 crore. So then we found that it is actually like not worth of doing it that way. When I try to develop even an intelligent control, that intelligent control is supposed to give a low cost and it is implementable in a simple processors or controllers. For example, if I try to develop even the GPU, which would be as smallest like ARM processors or probably you can say onboard PCs like Jetson Nano or you can say Raspberry Pi, that kind of processor I should able to adapt and run it. So then you see there are several questions will come if you think about designing. Okay. So when you think that way, although we said, so the development of, or you can say the intelligent control will work purely based on behavior. But when you talk about controller design, then we will go back with the old days. What old days? So you say that first of all, you have to understand the system dynamics. Then you will say that what you are again going back. So you said it's a lazy man, and you are saying that understanding the system dynamics. Yes, so then only you can actually make what we were talking about the intelligent control design for a lowest or you can say uh, better way, which will give least cost and better performance, all those things. If you want, then you have to think this. Whenever you design a controller, what would be the first prime most parameter you think? The system stability, right? So after that only you will see the you can say control performance and all. For example, your error and energy or time, all those things you will see later on. First the system supposed to be stable, right? So then only you can see the next performance. So in that way, if you look at the same way intelligent control design, although we are saying that there is no model required, but if you are able to understand the system in either the form of physical prototype and run and feel it, or you develop a mathematical model and try to generate a number of data. That is what we are trying to see. Then you can see the understanding the system dynamics can be done based on modeling and simulation. So there are several packages are available. For example, you talk about robotic system, you can actually like go to a virtual prototype like a ROS or probably MATLAB, robotic toolbox, that kind of thing you can bring it. So then you can actually like analyze the system behavior and then you can refine the control strategy. But what really the third thing is important. So the intelligent layers. So you put layer by layer so that you can actually like make your algorithm so flexible and so evolving in a learning base. So then you have to bring it the intelligent layer, which will give adaptability and self-evolving or self-learning, and it will give a decision. Oh, I need to learn further, or I am actually like already done. Now I have to use this data for executing further on. Like that, this call all will happen based on several layers. So these all important. So that's why I put these are the key element. You have to understand the system dynamics, then you have to perform modeling and simulation, then brought the intelligent layer where you have to put several fuzzy set or neural network or some kind of algorithm which make system better. So then you got the element, right? So then when you saw the element itself, there are several algorithm and approaches, right? So if you look at that way, so there are several popular approaches are available, which you have already studied in a different term. For example, fuzzy logic controller, you would have studied in introduction to AI or probably in a soft computing itself. Okay, for example, you talk about washing machine. So the washing machine control, in the old days, it is a fixed on-off control, right? When it evolved, the intelligence has brought in based on simple fuzzy logics. So that means simple linguistic rule can handle. Okay. For example, the power cut. So then the washing machine will immediately trigger that it frees the timing and where it stopped. When you restart with the power on, it won't actually go back from zero. It will start where it's stuck. So that kind of intelligence we brought in. The same way you brought the neural network based controller. So this is actually like what we discussed earlier, right? For example, the system diagnosis or you can say condition monitoring. These all required some kind of database so that you can predict. So how the behavior will come and then you can adapt accordingly. So the same scenario, if you look at it, adaptive controller, there are multiple adaptation, okay? Whether it's a direct adaptation, indirect adaptation, model-based adaptation, or simple feedback-based adaptation, like that, several adaptation is there. But when you talk about adaptive controller, so one thing, it adjusts the parameter. For example, you talk about robotic controller. So when the robotic gripper is picking some object, the payload or you can say the weight of the object doesn't know, but your adaptive controller sense the system variation, system state variation. From there, say that, oh, I lifted probably 2 kilogram payload. Okay, now you adjust your control parameter to compensate that. So that is what we call adaptive controller. Several times we use some kind of optimization. For example, the GA or you can say RSM or you can say PSO, those kind of optimization schemes we have used, right? So this will help several scenario. For example, you talk about motion planning of a mobile robot. So the obstacle avoidance and the path following is required. There are multiple objectives are coming. So when you put it in this, you can say genetic algorithm or PSO or you can say RSM kind of thing. So it will evolve and as well as it will give a better intelligent control outcome. So that is the way the genetic algorithm work. The similar scenario, if you look at it, the model predictive, which is we call conventional controller, but here the optimization scheme can be brought based on soft computing. So then it can actually like work effectively in a constraint system. For example, a simple process control system uh, for example, chemical industry or something. So then this model predictive with intelligence will work very, very high level. Okay. So that way, if you look at it, the reinforcement learning I already told, right? So it will give rewards and you can say penalty. It can actually like adjust and go. So the RL based is very popular in robotic platforms, mobile robots, even in autonomous car or you can say factory automations and all. The hybrid controller is little above where you have used all those things. For example, reinforcement control algorithm with MPC, or my student who worked so reinforcement learning with optimal control. Those things are actually like very well gel, and it can be developed in any complicated system. For example, the mobile manipulator, which is very complicated, but this particular hybrid controller work very well. Okay. So now you got idea. So what kind of different control approaches are available for intelligent controller design? So if you put that way, so you have to see the sequence, right? So first you have to define the objective. I already said the primary objective for the controller is the stability. So after that you put your specific requirement. For example, your actuator should not get hit the saturation limit, and my actuator should not run continuously, and it should not chatter, and my performance should be least you can say error, so and less energy, like that if I put, so then I can formulate the problem. So then I have to collect the different data based on the real prototype or in a simulation data, and then you train the model, and then actually like you put it in a validation stage. So then your algorithm is actually like now ready to choose. So you can actually like try to bring it either CNN or ANN or RL based, whatever logic you want. You can actually like choose appropriate intelligent method based on the application. Then you can actually like put it for a system identification. Then it will develop a crude mathematical model, and then it will improve based on the data driven, and it will ready to, you can say, implement and then evolve, and finally you can actually like perform for a final validation test. So this is where the step by step. So one of the easiest way you can actually like feel it. For example, you want to think about a mobile robot control. So one of the bigger problem will come in mobile robot, the state estimation. So because the GPS will not be available inside the uh, lab environment or indoor environment, and then you have to deploy either LiDAR or IMU. The LiDAR has a problem with multiple reflection. Even the its own, you can say, reflection will give another obstacles. So then it is a bigger problem, and IMU will have a huge drift and sensitivity, or you can say simple offset drift. So that also will affect in the overall performance. There, if you use this kind of intelligent control where your probabilistic based control scheme was improved based on the data driven model, then what happened? Your SLAM or whatever scheme you are developing would be high level intelligent. For example, Google has come with a deep mind, so that can kind of thing you can actually like broad, so then it can work better for the mobile robot. So that way what we are actually like seeing, if you put that way, the bigger challenges will come, because what you are actually like developing, that would be in a lab scale, right? When you are actually like putting it that into a large scale, for example factory shop floor or a bigger system. I developed for a mobile robot a small, you can say 20 centimeter by 20 centimeter, but now I want to develop for a earth mover. So then that may not work, right? I have to ensure that the controller is scalable and it can handle a large system, large or heavy system in an efficient manner. So this is a bigger problem. Then the real-time implementation, I already told, in a simulation it is easy, but the deployment is actually like very difficult. So even you can actually like check. Now we are talking about intelligent controller, right? You just Google it now. Even today you would have seen that some of the top journal, one or two paper would be published on controllers specifically to certain application. For example, you talk about underwater robot, even one or two paper in every day in a controller aspect would be published. Then you can see that in a year, it may be 200, 300 paper would be published in that particular domain. Why these many papers are coming? If you look at it, so one of the bigger problem is whatever the you call paper published one may not be directly implementable in a, you can say, commercial environment, or probably a factory shop floor, or even in a real-time prototype. It may be applicable for a certain class, certain vehicle, or certain situations. So that means there is a huge gap because the robotic or the real system is fortunate or unfortunate that it is in a real environment. The obstacles and the environment is having a disturbance, and the physical system is prone to be uncertain, and the sensors are prone to be process and sensor noises. So these all need to be avoided, and that's why even every day people thinking about, can I develop a big achievement to make sure that easily implementable controller that is still evolving. So that means if you look at it, even intelligent controller design, the real-time implementation is the bigger problem. In a simulation environment, it work better, but deployment stage it may back. So we have to see how you can develop your intelligent control, which can be deployable comfortably. In that direction, you can see that when you try to put a self-evolving controller, so several places even you will not get a clearance. For example, now you think about aircraft, think that you develop a high level intelligent control, even you validated in a lab environment, and now you are going for a certification into a aviation industry, or probably we call Ministry of Aviation, right? So imagine you are going for a certification. So the first question the certification uh, entity will ask that, do you have any fixed term controller? If you say no as a backup, so then your scheme will not be even evaluated. So that means you have to ensure your controller is actually like reliable, and when you implement this controller, the environment and the system is safe. So that you are to sure. I'm not talking about the self-evolving, which is like the robot movie. That is also another problem. But I am actually like saying that even the self-evolving can create a problem in several places. For example, when you think about aerial robot, your self-evolving is happening, and suddenly some communication happened, or probably it is in a cloud, the cyber security issue happened, somebody hacked. So then there is a huge problem, right? So that is the issue. And similarly, the data availability is one of the bigger problem. So developing method to design controller with unlimited data is a huge task, because although we said that it will evolve its own, but still for basic evolution, you have to think. So you know, right? These humanoid robots are very popular in even 90s, right? But as of now, we have not achieved what we dreamed about. So this is a bigger problem, because the data which is available is very limited, and as well as the evolution which you bother know, that is not that friendly. So that's the bigger problem. The expandable or even the explainability is bigger issue. Sometimes how this control algorithm work, only the developer will know. Even the developer will not able to explain to the even the user. So that kind of problem was there. So then you have to make sure that your algorithm is trustworthy, and anytime the debug can happen. For example, any bug is there, the user can debug it. That kind of problem solving capability should be there. And now we are moving towards industry 4.0 to industry 5.0. Then what happened, we are actually like fortunate to put it into the cloud. So then your intelligent controller can be sufficiently friendly and flexible to enable the cyber physical system. Okay, so that means it can be decentralized and as well as distributed control system, which enable the edge computing and IoT part. So this is the bigger problem. Even you would have seen, so vehicle to vehicle interaction, and then based on this vehicle to vehicle interaction, the vehicle control enable, right? That is where edge computing happening in the intelligent vehicles, right? So that means actually like your system should be very flexible to integrate these all that. If you put these all, the design of intelligent controller would be the worth taking, and as well as you can realize. As I already told, I gave a brief idea how this system will evolve and what are the important entities. So I hope now you got idea what would be the scenario. Since the audience level is different, I don't want to put it. So our own attempt in probably like vehicle manipulator or marine robot. So then that is a very you can say specific. That too we have applied a very specific control schemes. So then it may not be a very generic problem. So that's why I put up to this. So now if I have any questions from audience, I can handle. Otherwise, we can actually like move further. Ravi, is there any questions as of now?
Yes.
Hello, sir.
Ah, yes.
Minute.
1 minute. Sir. 1 minute, sir. I'm giving the participants. Yeah, participants, if you have any questions, you can unmute your mic and you can interact with the resource person. Professor Santha Kumar Mohan is available. Yeah, hello. Yeah, participants, if you have any questions, you can unmute your mic. Sir, one question they are asking, how to validate if the RL answers are correct?
So this is still open end only. You see,
In
you have
chat
to
box, they
only
have
validate.
written.
Yeah, no, that's okay. I'll just check. So you see, RL algorithm validation only the idea, because what penalty you are giving and what reward you are giving, right? That makes sense. So the success rate only make the system much more evolve, and then you can make it happen. Your success rate even 90%. So now you are giving a new scenario. It is not ensure that you will get again success for the new environment or new situation. So very simple example I will give. So for example, our students try to develop RL based algorithm for a mobile robot motion planning. So they prove that 10 situation, and then it is 8 situation was success every time. And when they did it in front of the evaluation, so where the BTP committee, BTech project evaluation committee, they asked that, okay, this particular scenario, can you test it? Then the student said that, sir, this you can say the room was not already trained, so we will check. So the robot we started and give the logic, you go this point to this point with this obstacle, and this robot is actually like keep on failing. So even the evolution stage, or you call the evaluator, gave 10 minutes for them to even sort it out. So even they are not able to do it, although their demonstration in the previous attempt, even in an open arena and all, it was showing the success rate of 80%. But the new environment comes, you don't know whether the success rate is ensured to succeed that attempt. So that's why the RL, whatever you ask the question, so you cannot trust. So that's why even the Google developed the DeepMind, right? So even that has a success rate only 50 to 80%. So when you get 100% success rate, so then only you can actually like confirm that. So this is actually like working. Okay.
Sir, another question they have asked. Can you give real-time application of PID and PD controller in design, sir? Yeah, participants, you can switch on your mic. You can interact with sir also, no problem.
No, PID and PD is actually like very popular in any system. For example, even you take a aerial robot, you use the Peacock software, right? Or you can say control unit. So inbuilt, if you open inside, so there is an inbuilt PID. Because PID is reliable, and because of PID reliable, people are using. Sometimes the PID, the I term can bring it some kind of crankiness. So for example, even a robotic system, people try to use only PD. For example, even you go to a KUKA or ABB, the conventional mobile manipulator or manipulators, so it would be by default PID control. So even your lift, so your day-to-day elevator, right? So that would be based on simple PID controller. So these are the example which you can actually do it. So now you can actually like see your lift is actually like coming faster or slower. Sometimes it go up and come down. So these are the, you can say, criteria you set, and based on that you can tune your KP, KI, KD, so that you can actually like stop and faster and stable, right? Like that you can actually like do it. So then there is another question based on our own reward can be novel and can I publish the paper? So if your reward algorithm, or you can say how you make the reward, and then so what algorithm you are using, so certain level it can be considered as you can say a delta contribution. I cannot call it completely novel, but there is a new contribution. Definitely you can try for a you can say journal paper. Only thing you have to experiment it and then validate. Then only the you can say success rate of a journal publication would be high. So is there any other questions? So
Sir,
if not, if I will just add one more
yeah, please.
slide. I already told, right? So I
Yes,
just
yes, sir,
add
please.
one more slide. So in my area, and then I'll just give a idea what where we are actually like leading. So you can see, right? So there are several chances are coming. Imagine. So imagine. So you see multiple hands are there in front of that. There is a donut or you can say vada is there. So how the hands are handling, it is purely based on the intelligence and swarm coordination, right?
Yes, sir, yes, sir.
Now, if you are thinking the similar way, there are multiple mobile robot agents. So one to another is just communicating. It's not predefined. Okay. So now you can see that each robot is evolving, and you can see like how here it is moving the same way. This is happening. This is what we are talking about intelligent control. It is based on the group target, and each robot trying to see that, so where is the, you call, the targeted vada or donut. Okay, for example, now all the robots commanded, so some of them are actually trying to find, some of them are still searching. Once some of them are found and then trying to push it to the goal, and during the evolution you can see that multiple robots are actually going back and coming. So this is the problem which the previous one audience asked, no, or you can see that not everybody is actually continued and pushing it, right? How the ants are doing, so ants are having a bit of intelligence, right? So the same intelligent level only the robot also having. It is not human being everything is able to process and then pushing it further. So it is not like that. So this is where we are actually like seeing the intelligent control design is evolving, and we are trying to see how the nature is there, the very similar way we are trying to put it. So in that direction, if you look at it, one more also can come. For example, so the group of ant taking together, right? So comfortably, it will not even a problem. For example, when they are taking a log, so it will go comfortably. The same thing, if I put it, for example, two mobile manipulator carrying a probably a lamp post, if these two are autonomous robot without any predefined collaborative target, it may fail, right? So if I talk about intelligent control, if these two carry and you can say post it in a proper location, it's a huge challenge. This is where we are trying. The same way you can see that the two of the manipulator jointly working without communicating to one to another. Here you can see that this is actually like homogeneous manipulator. Here heterogeneous manipulators. So, but these two supposed to do a collaborative task. How human being, for example, myself and Ravi is handling one board, so we will able to handle. But now imagine the manipulator is supposed to handle, so it is not that easy, right? So these are the challenges which put forward. If anybody was looking for a direction of problem, these are the interesting problem which is most of the robotic community people are looking in terms of intelligent controller part. Okay. And one of the bigger issue which is coming when we talk about future robotics, definitely intelligent control is one of the bigger issue. But there are two subsets. One is the repetitive task like
Yeah,
and
please
here
mute
you
your
can see
mic.
that
Hello, please mute your mic. I think Sari is telling very important information. Please mute your mic. Yes,
so
sir.
in
Yes, sir.
that sense, you can see that it's a repetitive task, right? So here the intelligent level is supposed to be less. It's supposed to do only a routine task. But here you can see that it's supposed to be a companion. The self-evolving also required. I choose the picture in such a way that you can see this this head is actually like open and here you can see closed. And that if you closely watch, this robot already know after this girl lift the coin, it knows that what it's supposed to do. It's a small smile also there in the face. So that intelligent the robot supposed to be there. So when you talk about you can say the challenges and the you call problem statement, these are the directions which you can evolve, and then you can see the focus of the roboticians moving towards this direction. And I end with this particular slide as thank. So I hope the challenges you got idea, and you are getting some clarity how to design, at least how to approach the problem.
Yeah. Participants, anyone have any questions still?
So RL cannot be better. Okay. So when it would be better when the traditional motion planning fails. Okay. So where you cannot develop, for example, SLAM. So SLAM is conventional, right? But it takes some time actually like long, and as well as it will not even give the localization properly. So then the RL based algorithm can be improved. So that's why I said so the RL cannot be just like that, take it granted. So somebody try to open and ask question, please.
So they're defaultly they are opening.
Okay. Okay, then I will close my side.
Yeah, yeah. Thank you,
I
sir.
hope it
Thank you.
was
Yeah, thank you for accepting
informative.
our request. Thank you, sir.
Yeah.
Thank you. Yeah, yeah. Thank you. Bye, sir.
Thank you then. Bye. Take care.
Thank you, sir.